Hey y'all. So I did not get to finish the two topics from the bacterial growth session, so I will do those two first and then I'll move on to sterilization. So these are the topics that I will be covering this session. I'll do dilutions, then media, and then the rest of this is from sterilization. Okay? I'll cover dilutions first. So I'm going to explain, I'll mainly be focusing on serial dilutions, not individual dilutions, but you kind of need to understand individual dilutions first before understanding serial dilutions. But let me just define this first. Okay. So your stock solution is basically before the dilution. And whenever I say dilution, it's like you're making something less concentrated. Like, for instance, bleach. If you got a container of bleach, you're not going to, I mean, depending on how bad it is, but let's just say that you needed to clean the surface top, okay, but you didn't want that you don't want that odor to be super strong, or you need to dilute it some with water. So you want to you may end up doing 3 parts water, 1 part bleach, so that maybe if it gets on your clothes, it won't do as much damage. You know what I mean? So that's what I mean by diluting, and you're making something less concentrated. So in that case, with the bleach example, the bleach in the container is considered the stock solution. Okay, before the dilution. Solution. And then the final solution, this will come into play, the serial dilution. But yeah, in the stock solution, that would be like C1, V1, like the initial concentration, the initial volume. The final solution would be C2, V2, and then the final concentration, the final volume. Okay, and then diluent is the fluid used for the diluent is usually DI water, distilled water. Okay. So now that I have that defined, maybe y'all are familiar with the formula C1V1 equals C2V2. If the C's kind of bother you, you can use M, like 1V1 equals M2V2. I like to use this one more because it reminds me of molarity, because that's technically the unit for this is molarity, and molarity is moles over liters. So or you can think of it as molarity, the number of moles of solute over liter of solution. Okay. And let's say this is your stock, and then this is your final. This is how you would label. This would be your stock, your V1M1. Final would be V2M2. The V2 is the volume of your final solution, and your M2 is the concentration of the final solution. So your M1 should be greater than your M2 because the stock should be more concentrated than your final solution. So the stock is more concentrated, which is your M1, right? And then your V2 should be greater than your V1 because you use the diluent to dilute the stock solution. So if I'm going, yeah, I'm saying this is my stock solution, right? And I want to take 2 mils here and add it into 3 mils DI water. So this 3 ml DI water is your diluent. And then your 2 mils, this is your V1. And then your V2, if you only did this, like if this was the only dilution that you did, you only took 2 mils from your stock and you put it into 3 mils of DI water, then in this case your V1 is 2 mils and then your V2 for your final solution would be 2 plus 3, which is 5 mils. Okay, but if I chose to do I did 2 mils here, and this is all still 3 mil DI water all the way down here. Okay, so if I had 2 mils transferred into 3 mils, then transfer another 2 mils from over here into 3 mils, you know what I mean? Then you're going to have a dilution for each of these. So you're going to treat you're going to treat this like, okay, you got your V1 here, and then your V2 there. So in this case, V1 is 2, V2 is 5. The same thing is here, though, where the volume of the first one that you're transferring here is also 2, and your V2. You're treating this one like the initial volume, kind of like how you did with the stock. The amount that you're transferring from this tube is your V1, which is 2, and then your V2 is, the volume of the final solution, which you're treating this tube as your final solution. So whatever tube you're transferring that amount into would be considered your final solution. I know it sounds a little bit confusing, so I'm going to explain a little bit more. So y'all understand this, right? A key to finding, like in serial dilution, you normally need to find a certain concentration or a volume, or in lab you might just need to say like, okay, do a 10-fold dilution. Like, what does that mean? If I say do a 10-fold dilution, then that's equivalent to saying an n-fold dilution. So your n here would be 10. So n is 10. Okay. Now, how do you find your n-fold dilution? By this equation. So let's say that in the question you were only given volume. You weren't given any concentrations at all. Then you would only use the V2 or V1 to solve your n-fold. But if you're only given concentrations and no volumes, then you would use this side of the equation to find n-fold. Now, the dilution, if the question just asks for the individual dilution, then all it is the reciprocal of your N. So, okay, dilution, I'll say individual, like for an individual tube, not like for all 4 tubes or something that you're doing the serial dilution for, is 1 over your N-fold. Okay. So I have an example problem for you to kind of help with this. I noticed basically, okay, if you didn't know that you need to do a tenfold dilution, or that, well, actually, no, that could work too. I'll do that with this problem, actually. So, example, so it would be perform a tenfold serial dilution. Okay. So this is your stock. This is 0.9 milliliters. You transfer 0.1 milliliters. 0.9 mils here. So we have 1, 2, 3, 4, 5, 6, 7. Okay. And all these have the same amount of diluent. 0.9 milliliters. And you transfer the same amount each time, which is the 0.1 mils. Okay, and then you're given that the concentration, the stock solution here is 10 molar. And so if you convert that to just plain molarity, that's you divide by 1,000, so it's 0.01 molar. Okay, so we were given tenfold here, so we're saying N is 10. But if you're not sure about that right off the bat, then we can double check our work. So for N-fold, we were given all these volumes, right? We weren't given individual concentrations. So that means we're going to do the M1 over M2. Oh, sorry, I meant V1, or V2 and V1. So the volume of our final solution here, you could choose, I'm going to choose these first two, okay? So the volume of my final solution here is it's going to be it's going to be the volume of, yeah, we can do, or actually no, that's fine. I'll just do stock and tube 1. So V2 is the volume of tube 1, which is 1 mil, because 0.1 plus 0.9 is 1 mil. And then the volume of the V1 would be our stock. And so the volume that's being transferred, so this is the volume being transferred to tube 1 is 0.1 milliliters. So 0.1 is equivalent to 1 over 10, so 1 divided by 1 over 10 is 10. So this just said that the N-fold is 10. So that does match up with what the question did say. Okay. Then if you were asked, if the question also asked like, oh, what was the dilution for tube 1 or what was the dilution for tube 2, then all you have to do is just take the reciprocal of 10. So I'd say dilution for tube 1 is 1 over 10. Dilution for tube 2 is also 1 over 10 because the individual dilutions for each of these tubes is 1 over 10 because you do 0.1 over 1. That makes sense, right? Because the biological dilution is the amount transferred over the total volume. So you're doing 0.1 over 0.1 plus 0.9. So it's 0.1 over 1, or just 0.1, and 0.1 is 1 over 10. So that's the same thing. So there's different ways that you can deal with that. But anyway, so let me get back to the original question. So performance tenfold serial dilution, okay. And now the question's asking what's the concentration of tube 7? So what's the concentration here? Well, since we know our N-fold now we can find the other concentration. So from that formula I showed y'all, we did M1 over M2 equals E2 1. So we already used this, that's fine. So now we know this, and we know the concentration of the stock solution. So now we're just looking for this for the 7th tube. But you have to take into consideration the dilution for all these combined. So to go from here to here, we did a tenfold dilution, right? Here to here, tenfold, here to here, tenfold, here to here, tenfold, and so on. So we have 7 tenfold dilutions. Okay. So what you can do is you can do the total N-fold, which is basically I just did 1N, so the N-fold for tube 1 times the N-fold of tube 2 times the N-fold of tube 3, etc., until you hit the N-fold for 7. So all you're doing there is 10 times 10 times 10, yada yada. So the total N-fold, so the total N-fold is 10 to the 7th. Okay. So with this, then you can find the concentration based on this formula here. So now you do 10 to the 7th equals, and we have the M1 is the original concentration, so that's 0.01 molar all over M2, or you can write M7 if that makes you feel better. So now we try to solve for M2. So it's 0.01 all over 10 to the 7. And so whatever that is, that will be your answer in molarity. Sometimes you may need to leave it in millimole, or it just depends. Okay, so I know I threw a lot of information at you there, but let's see how much time we have. Okay. Well, let me just review what we did here. So in this question, it gave you the N-fold, but I showed y'all a way to double check, like in case the question did not give you N-fold, how to find N-fold, and that's based on what they give you in the problem. So since we didn't have a final concentration, we used the volume. And to double check that, I did the V2, like the final volume in this case, I used as tube 1, and the original volume was the amount transferred from the stock, which was 0.1 mil. So the final volume from the amount transferred to tube 1 was 0.1 plus 0.9, which is 1 mil. Then here, the V1 was the volume being transferred from stock to tube 1, which is 0.1. So 1 divided by 0.1 is 10. So this is our infold, tenfold. And now that you understand basically the dilution for each of these tubes, as long as the infold is the same, then as long as the infold is the same for all these tubes, then all these tubes have the same individual dilution. That individual dilution is the reciprocal or the inverse of 10, or of the infold, which is 1 over 10. And I showed y'all a way to double check that in case you're not sure. So dilution for tube 1 was 1 over 10. And to check that, you do a biological dilution. So 0.1 was in the numerator. The amount transferred to the numerator, then the total volume in the denominator, which is 0.1 plus 0.9, which is 1. And then 0.1 is 1 over 10. So that matches there. Then, now you have your infold, you know your individual dilutions. Okay, good. Now the question is concentration of tube 7. To do that, you could go individually, like 1 by 1, with the M1 V1 equals M2 V2. Like you could do that individually down the line until you hit tube 7 and solve for M2, or you can do what I did and do the total infold for this whole thing. Now it works this way because the infold is the same all the way down the line. So from here to here was a tenfold dilution. Here to here, tenfold dilution. Here to here, tenfold dilution. All the way down. So you just do 10 times 10 times 10 times 10 times 10 times 10 times 10, which is 10 to the 7. My total infold dilution is 10 to the 7. Therefore, this matches up with this equation here. So all I do is plug and chug 10 to the 7 equals, and then my initial concentration was 10 millimolar, which is 0.01 molar. It just depends on the unit that you want to use. I just stuck with molarity, so I converted it there. So 0.01 molarity divided by M2, which is the final concentration. And so that's what we're looking for, the final concentration in tube 7. And I just rearranged that where I multiplied by M2 on this side, then divided by 10 to the 7. So now I have 0.01 divided by 10 to the 7. And you just use your calculator to find the decimal for that. So that's all. That's pretty much my explanation for dilutions. And now I'm going to briefly talk about growth on media, so I can move on to sterilization. So the 4 main types chemically defined complex media, selective, differential. I have a handout to show y'all too, but just to write out some simple definitions for this. Compounds to distilled water. DI water is distilled water. That complex you use enzymatic digest. Substances. Those substances can be like milk, yeast, or beef. Okay, and then in contrast, the exact chemical composition is, or the exact composition selective. Basically, you're saying that media favors growth of particular microbes. And then differential is media allows differentiation between groups of microbes and tentative identification. So I wrote these out just so that y'all would have some basic definitions for these. And now I'll show you the handout. It's just one page, and the way to learn this is, yes, the name, but you just want to make sure that as you're learning these, like, okay, they're, like, all these are complex in addition to being maybe selective or differential. Because you maybe ask someone to test, oh, which of the above are complex? And then you have a long list, but then which of the above are differential? So that would be 5% blood agar, ectone enteric medium, EMB, eosinophilene blue, the conky. Yes, that's it. So, but also the use is important as well. So it's just, it's just a matter of study skills at this point, like knowing, being able to learn this chart and being able to group. If you're able to group things, that's helpful, but the way I did it was I tried to learn them individually, and then I grouped them more. So this is more of a repetition technique, is you just got to keep reading over it, try to either say it to yourself, write it down on a whiteboard, or you can do individual flashcards for these if you want. It's just whatever floats your boat in that case for studying, but this does require practice and time to study. Okay. Alrighty, so that pretty much wraps up the bacterial growth part for this, and now I will be moving on to sterilization now. Okay, now starting on sterilization, is the first thing is microbial control. I just put some definitions here for sterilization, disinfection, high-level disinfection, antiseptic. Sterilization is the removal or destruction of all microorganisms, spores, endospores, or acellular entities such as viruses, prions, and viroids. Then disinfection is the elimination of most or all disease-causing microorganisms or viruses on inanimate objects. Some viable microbes may remain. High-level disinfection falls under this category. High-level disinfection is the inactivation of most vegetative bacteria, fungi, and a 6-log reduction of mycobacteria subspecies. So vegetative is usually relating to growth. So the inactivation of most, I would say, like maybe reproductive bacteria, fungi, and 6-log reduction of mycobacteria. Antiseptics, the destruction or inhibition of microbes on living tissue, prevents sepsis, and I put in parentheses for presence of microbes, toxins, or components in blood of host, and is less toxic than disinfectant. So for microbial control part 2, control 2 is involves decontamination, which is the treatment of an item to reduce the number of disease-causing organisms. And we have sanitization, and it is the reduction of microbes preservation. It is the process of delaying spoilage by impeding or blocking or slowing down the growth of microbes. A good visual for this is population. So this is sterilization, and then this trend would be kind of like goes out. That's disinfection. This one kind of goes up and over that antisepsis. So it's all a matter of the treatment of an item to reduce the number of microorganisms or disease-causing organisms, but it's a matter of how well it kills off or reduces that micropopulation. Also, I didn't have room for this, but pasteurization is the brief heat treatment to reduce the number of spoilage organisms and disease-causing organisms. So companies they pasteurize milk or ice cream. Ice cream is a common food that pasteurization that undergoes pasteurization. When selecting an antimicrobial procedure, you need to look at these factors, which I'm about to list. The type of microorganism, look at its population composition, the number of microorganisms, the desired conditions, such as pH, the presence of organic matter, and temperature. The risk of infection, the concentration of the chemical agent, and the duration of exposure. So there are different types of microbes, and based on that type of the type of microbe will determine how difficult it is for that microbe to be killed. So I'm going to draw this trend for y'all to show you the descending order of resistance to germicidal chemicals. I have to make sure it's showing that right. Clostridium, sporogenes, pseudomonas, Then we have mycobacteria. So mycobacteria is the plural form of mycobacterium. Another variation for mycobacterium is the Mycobacteria tuberculosis, Mycobacterium bovis, and then non-tuberculosis mycobacteria. Non-lipid or small viruses. Why do you think that whenever I say non-lipid, that could also be naked viruses? Non-lipid or naked viruses are more difficult to kill than lipid or envelope viruses because in a so in an envelope virus or lipid, you have that phage DNA, right? But surrounding this, and then here's your protein coat. This is the DNA. But then surrounding this is it's a membrane. It's a phospholipid bilayer. And then in a naked virus or a non-lipid virus, all you have is just this. You don't have a lipid bilayer envelope, and it's just a protein, so it's more difficult to disrupt the bonds in the proteins than it is to disrupt the lipid bilayer. So to disrupt this, to disrupt the membrane, you just have to add detergents like bleach or something, and that the bleach or the detergent would disrupt the membrane by basically taking bits. It would destroy the integrity of that membrane by taking bits and pieces of the membrane, forming micelles around it. And remember, micelles is the single lipid layer. Okay. So that was just more on the side. Virus, rhinovirus, fungi, trichophyton, subspecies Cryptococcus, subspecies and Candida. Vegetative bacteria, Pseudomonas aeruginosa, and then Staphylococcus aureus, Salmonella, cholera, and Enterococci. And then one more, the lipid or envelope or medium size virus. So it's the herpes simplex virus, CMV, HBV, HCV, HIV, and Ebola virus. So this is a trend. I put some specific examples to make sure you know this grouping of we'll definitely know that the naked viruses or the non-lipid viruses are more resistant to germicidal chemicals than lipid or envelope viruses. And just know this trend here, especially what I'm boxing in right now. So pretty much as you go down this line, it's saying like the farther down you go, the less resistant to germicidal chemicals they are. So bacterial spores, these are the most resistant to germicidal chemicals. Okay. So make sure that I got that. Now I'll go into the number of microbes, and I'll talk about D, like this is where D value comes into play. So for generation time, we talked about generation time is the amount of time it takes for the population to double. Well, D value, you need to think at, you can think generation time G as in growing. D value, you need to think as descending, declining. Because D value is the time it takes to kill 90% of microbes, or basically the time it takes to kill 1 log of microbes. So the goal here in sterilization is to kill microbes, right? Microbes are not immediately killed when exposed to chemical agents. It takes a little bit of time usually. Immediately killed upon exposure to agents. Basically, the D value is the decimal reduction time. D value. And that is the time needed to kill 90% or 1 log of microbes. Commercial canning, like for instance, Chef Boyardee soup uses the D value of 12. So, which means 10 to the 12 microbes are killed. Or like you see any of that canned fruit or other canned foods, like that's what they go through. And okay, so those are points to know about D value. Now I will show you how to find D value. Normally on the test, you need to be able to find the D value from the graph. Number of survivors. So I'm just putting these in orders of magnitude, and increasing orders of magnitude here. And I'm going to just draw a straight line for simplicity's sake. Okay, I'm going to draw a straight line, and pretty much what you do is, let's say, you'll be given a graph, and then you'll be asked, like, what's the D value? And in this case, since the line is straight, it should be relatively the same wherever you choose from the population. So let's say I do 10 to the 5. Okay. So let's say to find the D value, go down. Let's say this is 41. D value is the amount of time it takes to kill off 90% of microbes. So the time it takes to kill off 1 log of microbes. So 1 log would be a decrease in 1 order of magnitude. So I will go down 10 to the 4th because 1 log decrease from 10 to the 5 is an order of magnitude decrease, which is 10 to the 4th. And then okay, hi. Do y'all need help? Okay. What are y'all setting up for? Oh, okay. Hi. And then you go down to, let's see, I'll say that's 60. So that's saying between 1641, which is 19 minutes, 1 D value, so from here to here, between 10 to the 5 and 10 to the 4, that's 1 D value. And 1 D value is 19 minutes, okay? And if you want to double check yourself, you could pick 2 other points. So we can do 10 to the 4, 10 to the 3. So that's if, I mean, I do this freehand, so it may not be exactly the same. So 60, and then we decrease the 1 order of magnitude down 80. So 80 minus 60 is 20 minutes. So 19 minutes, 20 minutes. Like, that's pretty good for freehand. But anyway, so that was another D value. So this is 1 D value. So that's how you find 1 D value. But if, for instance, your graph wasn't straight, like this, so if you have the same unit, okay, log 10 survivors. Okay, so let's say instead of a straight line, you had more of a curve like this. What would you do? Because clearly your D value is going to change when the slope changes, okay? So let's say with the high-level disinfection, like what I wrote down a little bit ago, for high-level disinfection on mycobacteria, that causes a 6 log reduction. Okay, so 6 log reduction, that's going to be 6 orders of magnitude. So let's say we started off with let's say we started with 10 to the 7 cells for the population, okay? And then I apply high-level disinfection to this mycobacteria. So you know that it's going to have a decrease in 6 logs. So you're going to drop 6 orders of magnitude, which means you'll go from 10 to the 7 minus 10 to the 6, which will leave you with 10 to the 1, okay? But you can't just take the time from 10 to the 7, 10 to the 1, because if you subtract that time, that may be, the amount of time might be correct, but the number of D values won't, because for 1 D value, that's a drop in 1 order of magnitude, and each D value will not be worth the same. So if you're ever asked to find something like this over like a large change in the population, you have to go 1 by 1. Like I have to find 1 D value from 10 to 7, 10 to 6. I need to find the D value for 10 to 6, 10 to 5, and then I add them up. So to do that, I'll start with this. So I'm just going to say it's 5, okay, and then 10 to the 6, go down. I'm going to say it's 10, ballparking, okay? So this D value from 10 to 7, 10 to 6 is 10 minutes, okay? Then if I'm going from 10 to 6 to 10 to 5, this looks like it's 18 to me. So 18 minus 10 is 8 minutes. So 1 D value, 2 D value, that's already different, right? Then to 10 to 5, 10 to 4, go down. This looks like it's 21. So 21 minus 18 is 4. Oh, sorry, 3. Sorry, 3. 21 minus 18 is 3. So that's 3 minutes. Then if I do 10 to the 4, 10 to the 3, I'm going to say it's 25. So this will be 4 minutes for that D value. And then 10 to the 3 to 10 to the 2. Whoa, big change in slope, right? So this looks like it's, I'll say 45. So 45 minus 25 is 20. So it's 20 minutes. And then 10 to the 2, 10 to the 1. Well, this is supposed to be the line, but we're just going to pretend that's the line there. So I'll say that's 85. So 85 minus 45 is 40. So this is 40 minutes. Okay, so we have a total, and the question may ask like either how long it took for that high-level disinfection, or how many D values was it. It could be both questions. So for how many D values, it's 1, 2, 1, 2, 3, 4, 5, 6. So it took 6 D values to go from 10 to the 7 to 10 to the 1. And then how much time was that? Then all you do is 10 plus 8 plus 3 plus 4, so that's 15, and then 20 and 40. Okay, so that's 85 minutes. Yeah, 85 minutes. But if you had done this where it was like, if you just started from 10 to 7, then you did 10 to the 1, you got 85 minus 5, so it was 80. So it would not have been exactly right. So if you're given a graph where the line's not straight and you need to find either multiple D values or the amount of time, you need to go by the individual D value first. Okay. Now, prion sterilization and disinfection. So I guess first off, before I start talking about sterilization and disinfection, you need to know what a prion is. So a prion, I have a few bullet points I want to say about this, but basically it's a misshapen protein with no nucleic acids. Okay? So, and it's a hot topic to research, or it's been a hot topic to research. Infectious agent responsible for several neurodegenerative diseases found in mammals. I'm sure y'all have heard of the mad cow disease. Technically, the mad cow disease is bovine spongiform encephalitis, BSE. That's an example of where prions have a major role in causing that. Prions consist only of protein with no nucleic acid, no nucleic acid genome. Scientists know this because prions are resistant to UV radiation, and UV radiation usually disrupts nucleic acids. So, and since it didn't do anything, it didn't affect the prions, and that shows that prions do not have a nucleic acid genome. UV radiation breaks down nucleic acid. So, like I said, in the nutshell definition, a prion is a misshapen protein with no nucleic acid genome. Scientists have hypothesized that the disordered protein will bind to other proteins of the same type and induce those proteins to change their conformation or their shape, which will then cause a chain reaction that'll lead to new infectious material. Stored protein could bind to other proteins and induce them to change their conformation, like their positioning, as well, and then therefore producing a chain reaction that leads to the disease like mad cow disease, bovine spongiform encephalitis, and generate new infectious material. Okay, so there's my bit on the prion, on the characteristics of prions. So prion sterilization and disinfection, you want a 3-log reduction of prions within 1 hour. You want at least 3 orders of magnitude to decrease. The physical methods, which I will list out in a minute, are not optional. So the physical methods I'll list out in a little bit. You should not use those to sterilize, disinfect prions. The chemical methods work best. And the chemical methods that work best are sodium hydroxide and so some recommendations for prion sterilization and disinfection are to keep the instruments moist, decontaminate. 4 possible options are the autoclave, and I'm starting to get into the temperatures and times now, so make sure that you keep the times and temperatures straight with all these techniques, or methods. Methods is a better way to put that. Vacuum, autoclave, gravity cycle, tumors, 1 hour, and sterilize at 121 degrees Celsius for the gravity cycle, or 134 degrees Celsius pre-vacuum for 1 hour. Sodium hydroxide, 1 hour, and then 121 degrees Celsius, 30 minutes on gravity cycle. Clean again, and do 121 degrees Celsius for 15 minutes. So whenever I say the temperature, I'm saying like temperature for that amount of time. So the physical methods that I was talking about for the prions, so the physical methods I'm listing out right here: heat, pressure, filtration, radiation, removal of oxygen, dehydration, and mechanical removal, washing. Oh, this is physical methods. There you go. Okay, I'm going to do autoclave and pasteurization, and then I'll be out of time, and I'll pick up the rest of the sterilization topic in the next session. So, like I said, we're starting into the categorizing of the method, the sterilization method, with the specific temperatures and the amount of time, so you do not want to confuse those. This is another good list time if you want to make like one big T chart. If you do like the landscape mode, if you like turn your paper sideways and you just make like one big T chart where you have pasteurization, autoclaving, dry heat, prion sterilization, disinfection, and then you write down the temperatures and times just so you have it all in one place. Like I recommend that, or you can do flashcards. You can just read over and over it again, or you can talk through it. But like I said, whatever floats your boat. But anyway, I'm gonna do. I'll do autoclave first. So a lot of private practices and hospitals use the autoclave, and we at TMCC we have two autoclaves in the CS, and the autoclaves are used to. I know like at private practices we use the autoclave to sterilize the surgical instruments or any of the towels or cloths that are used in surgery. Anyway, what's happening in the autoclave is that heated water within the enclosed vessel forms steam. The steam increases pressure for it to be greater than 14 pounds per square inch, or 101.3 kilopascals. Water boils at a higher temperature. You definitely need to know this, is the standard 121 degrees Celsius at 15 pounds per square inch for 15 minutes. If you want to do the flash autoclaving, you do 135 degrees Celsius for 3 minutes. Prions inactivated at 132 to 134 degrees Celsius. So as you can see, the standard is lower than where the prions are inactivated. And for quality control, geobacillus endospores are used. Basically, there's geobacillus endospores outside the autoclave, and you put them inside the autoclave, and they're basically a certain color. They're basically a certain color before you put them in the autoclave, and then if the autoclave is working or not, then there should not be a color change. But if there is a color change, then that means that it's not working. Okay. So there are two types. So autoclave, there are two types. So the first is the gravity displacement autoclave. For the preons, when I was talking about the gravity cycle, I'm referring to this type. So steam at the top or side chamber. Steam forces air bottom of chamber through the drain vent, drain, less penetration, so longer sterilization time. The second one is called high-speed pre-vacuum sterilizers. Fitted with a vacuum pump or ejector. It ensures air removal and sterilizing chamber before steam is emitted. Increased penetration, shorter sterilization time. Honestly, the main difference between the two is the amount of penetration and how much longer or shorter the sterilization time is. But it really depends on your professor and how much y'all need to know about like where the steam is being forced out of and whatnot. But for my class, we mainly need to know that main part about the types of autoclaving. Okay. And last but not least is pasteurization. Pasteurization significantly decreases the numbers of heat-sensitive microbes. Significantly decreases the numbers of heat-sensitive microbes, including including pathogens like mycobacteria. Mycobacterium, tuberculosis, and Coxiella burnetii. Pasteurization is used for milk and juices and some household items. Pasteurization helps increase the shelf life of food. You can also pasteurize rubber mask for 80 degrees Celsius for 15 minutes in the washing machine. So there are three levels of pasteurization. So originally we had low temperature holding, low temperature holding, and that would be 52.8 degrees Celsius for 30 minutes. And then there's high temperature short time, high temperature short time. And so we do 72 degrees Celsius for 15 seconds or 82 degrees Celsius for 20 seconds. Depends on the fat content, like if you're going to do milk versus ice cream. Then we have ultra high temperature. So the whatever you're pasteurizing will determine whether or not you will determine which level of the pasteurization you'll do. Okay. Make sure you know that. Alrighty. So we're about halfway through pasteurization right now, and in the next session I will wrap up sterilization, and then we'll move on from there. So good luck studying. I hope this helped.